Okay, so we'll start with the winding number. So, so I hope the screen is visible. This sharing. Yeah. Okay. So yeah. So the definition of winding number is. So I will just repeat those things, recall those things, and then we will move towards the assignment problem. Okay. So let gamma be a closed rectifiable curve. So closed rectifiable curve in the complex plane C. Okay. And and z belongs to C minus this gamma. Okay, so this gamma is basically so if okay, let me first remark something. So this so we know that a curve is nothing but AB to C, which is continuous. Okay, yeah. So I will denote this curve gamma. I mean, uh, the trace of this curve gamma, or the trajectory of this curve gamma, as like this. So this means the trajectory of the curve, like this thing in the complex plane C. So this is trace of gamma. Okay. Yeah. So uh, okay. So let me come back to that one. Okay. So the winding number, the so the winding number, so the winding number of gamma about this point z. Okay, also this one is also known as index of index of gamma with respect to z. So this wording index is there in the Conway book. Okay, so this is defined by, so this is defined by, so for this class, let us use the same notation. So winding number of gamma about z is basically 1 upon 2 pi iota integral over gamma d xi upon xi minus z. Okay, so this is the way we define the winding number. Okay, so basically geometrically, winding number is nothing but the how much a curve uh, wind around a point. Okay, number of times a curve wind around a point. So I will just, okay, so this is about the winding number. Okay, so let us note something. So the trajectory of a path gamma in C is basically is what is a closed and bounded set. This means compact closed and bounded set. Okay, and the set. So the set, since it is closed and bounded, so this set is basically is this is non-empty open set. Okay, this is basically non-empty open set. It means that C minus gamma is nothing but a, let us say, union of U alpha alpha belonging to some index set where U alphas are nothing but disjoint union of domains. So this is basically a disjoint union of domains, okay, uh, which we call basically the components of. So these we call components, so the components of C minus gamma. These are we call the components, components, components of. Also, since this is bounded, this trajectory is bounded. This okay. So this C minus gamma has exactly one unbounded component. This is this, therefore exactly one of these components is unbounded. Okay, so this is fine. Let us look at towards the assignment problem. So question one. Okay, so for a curve gamma, and let z doesn't belongs to this gamma, okay, this describe, sorry, denote the winding number, by z. So which of the following are true? Okay, so the options are: first, gamma z is invariant under reparameterizations. Reparameterization of gamma. Okay. Now the second thing is W gamma of z is basically, so here gamma is a closed curve. Okay, is basically W of minus gamma of z. Okay. Third one is uh, W of gamma 1 plus gamma 2 of z is basically W of gamma 1 of z plus gamma 2 of z. And the fourth thing is, so I mean, so if gamma 1 is homotopic to gamma 2, okay, then if this, then gamma 1 of z, let us say z naught, yeah, so z gamma 2 of z. Okay, okay, fine. Next option is, so W gamma such that C minus gamma to, just say this is So uh, I think one can prove here, remark. So this we know that this is always an integer. Okay. I mean, one can try to prove this, or one can find in any book on this topic, Conway or Palka. So let me just write down the reference of this one so that if anyone wants to see, one can see the Conway book and BP Palka for the more detail on this topic, on the winding number. Okay, so this is is locally constant. Although I will not prove fifth option because this is also in this week assignment. So this I will not prove. Sixth one is sixth option is okay. So let us do it five. That I will later. Or should I write it down? Okay, fine. Solution. So recall that what is winding number. So this is nothing but integral over gamma I. Okay. Now if you take any parameterization of gamma, this integral will be the same, isn't it? This integral doesn't change upon the parameterization of the curve gamma. Okay. So first option is true, and in fact with this first option is true. Okay. Now if you look at the second option, uh, this let me write it down here. You just take 1 upon 2 pi I, or let us say 2 pi I into this one, t psi from xi minus z. So this is what? So I mean, once you change the trace of the curve gamma from so this is your curve gamma. If you do like this, the same curve, what we so what we'll get? This integral will be the minus sign of this one, isn't it? So this option is not true. Okay, because uh, I should okay. So so once we just retrace this gamma backward direction, let us say like this. Sorry, this would be like this. So this integral will be with the minus sign. Okay. So here the minus sign will come. So for option two is not true. So basically, what is true is okay. Regarding the option three option, again you just use the uh, fact about the integral of this function. So gamma 1 plus gamma 2 is basically the integral will be separated on gamma 1 and gamma 2. So this is also true and this one is also true. Okay, so let me just write down a fact about, or I should just, so let gamma from A to B to C be a closed curve. Okay. closed curve. So W of gamma is a function from C minus gamma to C. Okay. Now this, which is defined as W of gamma of Z, is nothing but 1 upon 2 pi I integral over gamma. We can write d xi upon xi minus z. Okay. So what I will prove that the derivative of this one. Okay. So the claim is this z is nothing but 1 upon 2 pi I integral over gamma xi minus z whole square. Okay. So this is our claim. Okay. So let z not be any point, any arbitrary point. Okay. Now let us calculate this one, z minus z naught upon z minus z naught. So this is what, 1 upon z minus z naught. This is, okay, so I will take 1 upon 2 pi I common. Okay, that we'll see later. Let us just xi minus z minus integral over gamma d xi upon xi minus z naught. Okay, so this is nothing but naught integral over gamma. This will be xi minus z naught minus xi plus z upon xi minus z into xi minus z naught d xi. Okay, and this is, so this z minus z naught will get cancelled out. Now I will, okay, so for preciseness I should write 2 pi I here. Here also 1 upon 2 pi I is there. Okay, so this is integral over gamma d xi, so xi minus z into xi minus z naught. Okay, now what we are going to calculate is z minus w gamma z naught upon z minus z naught minus, so minus 1 upon 2 pi I integral over gamma d xi upon xi minus z naught whole square. Okay. And we will see that at z tends to z naught, this quantity should go to 0. Okay. Means limit z tends to z naught of this quantity. So limit z tends to z naught of this quantity is basically equal to this quantity. Okay. So it means it is the derivative of this one. Okay, so let us do this one. So this is nothing but, so I will take 1 upon 2 pi common, and this will be integral over gamma d xi upon xi minus z z naught minus integral over gamma d xi upon xi minus z naught square. Okay, which is nothing but integral over this one. So this xi minus z naught square, let us write, so xi square minus 2 xi z naught plus z naught square and minus of xi square and z naught xi and z xi. So this will be plus xi into z naught plus xi into z, and oh wait a minute, So denominator part is xi minus z naught square into xi minus z. So xi minus so here it should be xi minus z naught, xi minus z naught minus xi minus z. So minus xi plus z. Okay. So it is just wait a minute. So the stake is there, I guess. Okay, yeah, fine. So, this will be modulus of z minus z naught into tail gamma d xi upon xi minus z naught square into xi minus z. Now again, what we will do, so we can find an r such that xi minus z is greater than equals to r and xi minus z naught is greater than equals to r. Okay, so this means that this quantity is less than equals to mod of z minus z naught upon r cube integral over gamma mod d xi. Is it clear up to this point? Any doubt? So basically this we can find because xi is on this curve gamma, okay, and the curve gamma is bounded always, so this we can always find. Is it okay? This is nothing but mod z minus z naught upon r cube into the length of the curve gamma. So this is ultimately constant, this is also constant, so as z tends to z naught, okay, wait. So it means that this quantity tends to 0 as z tends to z naught, okay, and thus we have this z naught is 1 upon 2 pi I integral over gamma d xi upon xi minus z naught square. Okay, so we know that the C minus gamma is basically is an open set. Okay, so this is an open set. So the C minus gamma is nothing but, okay, is the union of these components. Okay, so this Z naught, so these are disjoint, disjoint union. This is disjoint union. Okay, so this Z naught will belongs to some of this U alpha. Let us say U U, or just say Z naught belongs to U, one of such component. Okay, so what do we get? This Z naught is nothing but 1 upon 2 pi I integral over gamma d xi upon xi minus z naught whole square. Okay. Okay. So this, if we consider this function f of xi as 1 upon xi minus z naught, this implies that f dash xi is basically minus 1 upon xi minus z naught square. Okay, so this this quantity basically f dash basically 1 1 upon xi minus z naught square has a primitive. Okay, so this is that is, so this has a primitive in c minus z naught. Okay, so what would be the integral over the curve? So this has a primitive in c minus z. So what is the primitive? Basically minus 1 upon xi minus z naught. So what would be this integral? Please just let me know. I mean, the whole thing is clear or not? Okay, so now since this has a primitive, this integral will be 0. It means that z naught is basically 0. Okay, and and this means that gamma is constant on this component. Is it clear? So this, so whatever the component you will get, in that component at all the point, this W gamma is constant. Okay. Is it clear or not? Yeah, okay. Okay. Now let us see something. So now let us see an important case. So in this case, I will assume the Jordan curve theorem. Okay. This is interesting. Okay. So let gamma be a simple closed curve, since it is a Jordan curve. Closed curve, and and z naught be a point inside gamma. Okay, so a simple closed curve means this parameterization, whatever the parameterization it is, it has, it is simple means it is 1 1. Okay, so this curve will look like, in general it doesn't look like, I mean, the Jordan curves can be more complicated they are quite complicated. But I'm assuming here that Jordan curve theorem. So it means that it has some inside part and outside part. So it means basically it says that this Jordan curves separate the plane in two parts. One is inside and one is outside. So basically C minus gamma is basically, let us say, U star union V star, where this is bounded component and this is your unbounded component. Okay. Let us see that what would be the winding number for any point z naught inside this one of this simple closed curve. So our question is, what is this? Okay. So let fz is basically 1 upon z minus z naught. So clearly f is analytic c minus 6. So let us call this domain, this thing, as d, omega. So omega be the shaded region. Okay. So this is a domain. Okay. So basically z naught belongs to omega. Okay. So there exists R such that this ball closure R is basically contained in omega. Okay. So basically what does it mean? It means that, okay, so I will draw another picture. Okay. This is the shaded region, and this is the point z naught. This is the curve gamma. This is the region omega. Okay. So what we will get is, so we will get a ball of this radius r. Okay. So this is your r. Okay. So what we are going to do here is that let gamma 1 is nothing but mod of z minus z naught is equals to r. So this is your gamma 1. Okay. So this curve, this circle, okay, this is your gamma 1. Now let us denote, so, and let gamma 1 is equals to this, and u is basically z belongs to omega such that mod of z minus z naught is greater than r. Okay. So basically this is the u, this part outside this thing. So this whole part is your u. Okay. Now what we're going to do is, let us join them by a line. So let us consider this line. Okay. This is your point A to point B. Okay. So let omega, this is omega dash. Omega dash is nothing but u minus ab. Okay, so I'm removing this line from this u. Okay, whether this construction is clear? I have not done any fancy stuff in this one. So it is clear that, so clearly omega dash is simply connected. Is it clear? So this is your omega dash as, wait a minute, some mistake here. Okay, so omega dash is basically u minus ab. Okay, yeah, so I hope it is clear now. So this is simply connected. Okay, u minus ab is saying, so basically the, see, this u is not simply connected, because you can take a curve like this and it will shrink in this point. Okay, basically this u is not simply connected. You can take a curve like this in u, but it will shrink somewhere here. But once you put this line, you cannot take such curve. Okay, so you can take only this type, this kind of curve. Okay, here, so this will homotopic to constant curve. So basically this omega dash is simply connected. Okay, so okay, so let us say what would be the boundary of omega dash is uh, gamma 1. No, so gamma, let us define its direction. Okay, so now from this to, it will come here, again it will go to b. Okay, so from a to, it will go b, then b it will be from gamma 1, and again it will trace back from b to a here, and then again it will go like this. So I hope it is clear. Okay, so this is nothing but gamma. So not the complete gamma. So this boundary, you know, so this, so you will start from here, you will go to a to b, then again you will travel around gamma 1, then again you will trace back b to a, then again you will complete the curve gamma. So basically it's gamma is, the boundary is contained u gamma ab union gamma 1. Okay, so basically we are, this one is, basically this one is in, in a positive steps. Okay, okay, so what would be the integral of this one over this, over the boundary of this one, boundary of omega dash of this function fz? Okay, so integral over the boundary of omega dash d xi upon xi minus z naught is equals to 0. Okay, because this function is analytic in this one, and this is simple goes, so boundary of the Jordan domain, the boundary is simply connected domain, so this will be 0 by Cauchy's theorem only. Is it okay? what does it mean? It means that so over gamma will go and then AB psi upon xi minus z naught plus this will be so, yeah, so this is fine. Then this on BA also. So BA is nothing but okay. So BA d xi upon xi minus z naught plus integral over gamma 1 d xi upon xi minus z naught. So this okay, yeah. So this gamma 1, see the direction of gamma 1 is clockwise. Okay, so in this integral this should be minus gamma 1. Okay, so this is fine. Gamma is basically your this thing positive direction, then we are going A to B and then I'm coming back B to A. So this will be, so this B to A and A to B will be 0. So this whole thing is 0, but this combining this will be 0. So combining these two things, this will be 0. Okay, and the next we'll calculate. So this implies that integral over gamma d xi upon xi minus z naught minus integral over gamma 1 d xi upon xi minus z naught is equals to 0. So this means that integral over gamma d xi upon xi minus z naught is basically equals to integral gamma 1 d xi upon xi minus z naught. So this now this integral of over gamma 1 means here the green curve which I have written as circle gamma 1. So this gamma 1 is considered like this. Okay, so it is positive direction. Okay, so this integral is what? So this integral is always, we have seen also earlier, this is 1. Okay, so it means that this, oh, wait a minute, this we have seen as 2 pi I. So this will always be 2 pi I. Okay, so therefore what we have proved is 1 upon 2 pi I integral over gamma d xi upon xi minus z naught is actually 1 for every z naught belongs to this omega. So that if you take a Jordan curve, so this, if the orientation is your positive orientation like this, then this z naught inside the curve, inside this Jordan curve, the winding number of the curve gamma about the point z naught will always be 1. Okay. So winding of, so this, now here we can write it as, here we can write it as basically 1. So this is, so this was our claim. Is it fine up to this point? Any doubt, please let me know. Okay, if no doubt, then I will move ahead. Let us see the next question. Okay. prove or disprove, disprove following statements. So first is if fn is a sequence of holomorphic functions defined on a domain omega, fn converges to f. So this I will write pointwise. Fn converges to f pointwise to f on omega, then f is holomorphic. Second is if fn converges to f uniformly, formally on compacta. Okay, so uniformly or compacta means fn converges to f uniformly on every compact subset of omega. Okay, then f is holomorphic. Okay, third is suppose omega plus is basically z belongs to omega such that imaginary part of z is positive. Okay, and omega minus is basically z belongs to omega such that imaginary part of z is negative. Okay, so if a holomorphic function on if if f a holomorphic function of holomorphic function on omega plus union omega minus and continuous on the whole omega, then f is holomorphic on omega. Okay, so this we will see now. Okay, let us go towards the solution. So regarding the first thing, fn converges to f. So this is your pointwise. This is a pointwise convergence. These all fn's are holomorphic. We need to check whether f is holomorphic or not. So basically this is false. I think one can calculate examples quite easily. The main thing which I want to mention is the following result of Osgood, which is less known. Okay. So it says that, I think that is some paper and also math. Okay, so this says that this is just for your knowledge, or you can go through with this one. So let okay, so fn is from omega to c. So these are all holomorphic functions. Fn converges to f, that same thing, pointwise. Then there exists, if this is this, then there exists an open dense set, let us say D subset of omega, such that F is holomorphic. So it means that if Fn converges to F pointwise, obviously you cannot say that F is holomorphic throughout the domain omega. But what you can say is there existed open dense set on which F is holomorphic. Okay? So this is just for your information. Let us see the, okay, so the first thing is not true. Okay? Second thing, let us see. So I will go to the next page. So let Fn such that omega to c be a sequence of holomorphic functions, okay, such that Fn converges to F uniformly on compactor. Okay, on omega. Fn converges to F uniformly on compactor on omega. So clearly F is continuous. This is, there is no doubt in this one. So basically the idea is to use the Morera's theorem. Okay. So what we are going to do is, so this is, let us say, this is the domain omega. Maybe some points are removed or not there. Let us consider a disk, this, whatever the disk you can take in omega. This is the disk D, okay, and consider any triangle in this omega, this disk, okay. Okay, so consider any disk D subset of omega and triangle T in this disk. So since Fn converges to F, so since Fn converges to F uniformly on compacta, that is Fn converges to F uniformly on every compact subset of omega. Now this closed triangle, this is a compact set in omega. So Fn converges to F uniformly on T. Okay, whatever triangle you take. Now you consider this integral. Wait a minute. A better way to write is, consider this integral fz dz. Okay, this is nothing but limit n tends to infinity t fn z dz. Okay. Now since f is holomorphic, by Cauchy's theorem or Gauss-Hart theorem, we can say on this closed triangle, this each fn integral will be 0. So by Cauchy's, or you can also say Cauchy-Gauss-Hart theorem. Cauchy-Gauss-Hart theorem, which we have seen. So this is a closed triangle. This is equals to 0. Okay. So the whole thing will be 0. Okay. So on every closed triangle it is 0. By Morera's theorem, F is holomorphic. Okay. So the second option is true. Let us look at the third option. Is it clear or in doubt? I will assume there is no doubt. Okay, so let us denote omega as omega plus, union omega minus, and union I. So what is all these things? So what is your omega? Omega is kind of, let me write it down here. Let us say something like this. Your omega is this. Okay, and you draw a line. Okay, so this part is your omega plus. This part, this part is your omega plus. This part is your, I should write this part as your omega minus, and this part, this thing, I am calling this as I. So I hope it is clear. Different color. So this is your I. This is omega minus. Okay, is it clear? Okay, so what is your F? F is from, let us see. So if a function holomorphic on omega plus and omega minus. Okay. So let us say let F be holomorphic on, let F be holomorphic on omega plus and omega minus. Okay, so the claim is, we will claim that F is holomorphic on whole omega, holomorphic on omega. Okay, so the idea is to use Morera's theorem. Okay, and for that we need to do some construction. So see, uh, so what we need to show is, this is 0 for every closed triangle T in omega. Okay, so suppose if I take the triangle like this, integral will be 0. Okay, because F is holomorphic on this one. Again, if I take the triangle in omega minus, this integral will be 0. Okay, the only problem is of these triangles. Suppose if I take a triangle like this, okay, means which is touching this part, which is which is uh, touching this I, okay, or something like this, okay, or the thing is like, sorry, or one side, the whole side is on I. So we have to consider three cases. Okay, so let me write it down. Like small thing here. Let us, so we will consider this thing, this as one case. So this will be your something like, let us say this is one case, and something like this is your another case. Okay, and something like, let us say one touching point on this one, something like this. So these kind of triangles we will having in this one. Okay, let us try. try to do this one. Okay. So what we're going to do here is the following. This will be a little bit constructive, but anyhow we will do like this. Okay. So okay. It is a little bit tilt, but assume that it is a excess of this one. And we consider this triangle. Let us consider this triangle because this is the toughest part. Okay, and let's say this is A, B, and C. Okay, and we just construct a small rectangle on this one. And let us give a direction. Okay. And let us call it as B delta dash and C delta dash, C delta, and B delta. Just call it by some name. Okay. So we can always construct such kind of thing. We can always construct. We can always construct a compact set K such that this triangle T is subset of K, and since F is continuous, what we have as mod of Fz is less than equals to M for every Z belongs to K. Okay. Okay, let us consider this integral ABC. This is what T is, Fz dz. This is nothing but, so this is A, B delta and C delta Fz dz plus again B delta B C delta Fz dz. Okay. Now this is 0 by Cauchy's theorem. So this is nothing but ABC Fz dz is basically equals to C delta Fz dz. Okay. Okay. So since delta is arbitrary, means arbitrary is small, what we can do here is that integral ABC Fz dz is lambda limit delta tends to 0 integral B delta BC delta. This always we can do. Once delta tends to 0, this will cover the integral. Now let us calculate what is B delta BC delta of Fz dz, which is nothing but B delta dash Fz dz plus B delta dash C delta Fz dz plus integral over c delta dash c fz dz. Okay, so as delta tends to 0, the length of b delta b and b delta dash, this tends to 0, and length of c delta dash and c distance to 0. Thus we have uh, this integral b delta b and b delta dash fz dz, which is nothing but less than equals to m into mod dz of b delta b delta dash, which is nothing but length of b delta b delta dash. Okay, so this will tend to 0. Okay, and similarly this integrals c delta dash and c fz dz is also 0. So the only thing is this one. So the only thing is left is integral over b delta dash c delta fz dz. This is the only thing is left. Yeah, this part. Okay, now this thing is nothing but integral over b delta dash fz dz plus integral over v delta dash c delta dash fz dz plus integral c delta dash c delta fz dz plus integral c delta b delta fz dz. Okay. Now as delta tends to 0, again length of b delta and b delta dash, this tends to 0 also, and length of c delta dash c delta, this tends to 0. Okay, also when you have this one b delta dash c delta dash and c delta b delta, so this is b delta dash and c delta dash and b delta and c delta. Okay, so this is basically this curve and then this curve. So the addition of this plus this as delta tends to 0 will be 0. Okay, also this integral b delta dash c delta dash fz dz plus c delta b delta fz dz, this tends to 0. Okay, so these three things will happen as delta tends to 0. Now combining all this, integral abc fz dz is equals to 0. So this implies by Morera's theorem, we have that f is holomorphic. Okay, so I hope it is clear. If you have any doubt, just let me know. You can stop here. I mean, you can stop me here. We'll see some more problems on this one. Is it okay? So let's assume that it is fine. Okay, let us look at the next problem. So how to do this one? I mean, this theorem we know regarding the locally injectiveness of analytic function. I will just recall this theorem. So the theorem is, so let f such that omega to c is holomorphic if f dash z naught is not equals to 0, then there exists R positive such that f f is 1 on this ball. So I mean every if our holomorphic function, if the derivative is non-zero at some point, it means f is locally 1 1. Okay, so it is about the localness. So suppose f dash z is non-zero throughout the domain omega. It doesn't mean that f is 1 1 throughout the domain omega. For example, let's keep this in mind. So fz is equals to e to the power z. Okay, f dash z is again e to the power z, which is non-zero for all z belongs to C, but f is not 1 1. Not 1. Although by this theorem it is locally 1 1. So this is done, and others we can check for this one. Okay, just let me see. So this I will just record. We will go to the next problem. So the next question is, so this will be our last problem. Okay, so consider this function. So, so we have to compare this statement with the Schwarz reflection principle. Okay, so first I will recall the Schwarz reflection principle. So, so let me first recall the Schwarz reflection principle. So let omega be a plane domain which is symmetric about the real axis. Let G and G star G and G star be the components of omega minus r real line, and let I be actually omega intersection r. So you just remember this figure, okay, this kind of figure. So this is omega, and yeah, so this is, although it is not symmetric, because the way I have constructed this one, so it should be from again from here to go like this. But this kind of thing will be there. Like you just take the this kind of domain. So this is symmetric. This upper part, so this upper part and this part. So symmetric with respect to real axis. So let this one. Now, if f such that G union I to C is continuous and holomorphic on on G is continuous, holomorphic on is continuous, holomorphic on G and real valued on I, then so basically then one can extend f as a holomorphic function throughout the domain omega. Okay, basically then the function defined by function f such that omega to c defined by fz is basically your f of z when z belongs to G union I, and again f of z for this if z belongs to your G star. Okay, defined by this is holomorphic. I mean, we can extend f to capital F. Okay, so let us look at this problem. Okay, so let's look at this thing as a this example. So 1 upon I plus z. Okay, so this is holomorphic on the upper half plane, isn't it? So this is holomorphic on the upper half plane here. So this is holomorphic in this upper half plane, but it is not holomorphic in lower half plane. So what is there in the this Sauge fixation principle which this function is not satisfying that property? So can anyone tell me? So I mean this kind of function is not real valued on this real axis. Okay. So if you take this, these are the imaginary values. Okay, is it clear? Now let us look at the question. So, question is if if f is holomorphic on the right half plane, okay, if f is holomorphic on the right half plane, that is z such that the real part of z is positive, continuous on the imaginary axis, and if f takes the imaginary axis, that is imaginary axis to itself, I mean f of this is subset of Im, okay, then f is an entire function. Okay, so I mean, okay, which of the following are true? this is first statement. Second is f says that omega to c is holomorphic. So 1 1 holomorphic map, then f is a closed map. Okay. Third statement is f is f is non-constant holomorphic function on omega, then 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 f inverse omega f inverse k, f inverse k, that is f inverse of every compact set k is compact. Okay, this thing we have to see. Okay, so let us write it down as solution. So the okay, so now let us look at the option one. So f is holomorphic on, let us denote it as right half plane. Okay, so right half plane is z such that real part of z is positive. Okay, f is holomorphic on this right half plane and continuous on this imaginary line. Let us define a function from the upper half plane to c using f. So g of z is nothing but I of f of minus I z. I mean, so how does this work? If h is in h plus, that is z is equals to x plus iy, where y is positive. So what would be the iz? Iz is nothing but ix minus y. Okay, and again minus iz is y minus ix. Okay, so now real part of this one is positive, this one is positive, so iz, so minus iz belongs to this r. Okay, so now this is fine, f of minus iz. Now again you take i's, multiply with this one. So if you multiply a point in the right half plane with I, where it will go? So it will come to the, so let us say z is analytic in upper half plane. Okay, so G is analytic in upper half plane. Also, if Z belongs to this real number, real line, what would be G of Z? Okay, so if Z belongs on the real line, means Y is 0. Okay, so Ix, so minus Iz, it means minus Ix. So uh, minus ix will be on this imaginary axis. Now f maps imaginary axis onto imaginary axis. Okay, so f f of minus iz is again on the imaginary axis. Then if you multiply by I of the imaginary axis will again becomes the real axis. Okay, so g of z is again in real line. Okay, now we are in the Schwarz reflection principle case. Okay, so by Schwarz reflection principle, G is entire. Okay, means you can extend G using this one, this formula. Okay. Now once you extend this G using this formula, you can extend this F. So by square reflection principle, G is entire. So is F, and so is F. Okay. So I hope this is clear. Let's look at the next example. So the next option is, if F is 1-1 holomorphic map, then F is a closed map. Okay. So if F is 1-1, it means that F inverse, this is third option or second option. So it means that F inverse is also holomorphic. Okay. So this is just a inverse function theorem of this one. Now F inverse is holomorphic, so it is continuous. So F inverse maps by definition closed set onto closed set onto closed set. Okay, this implies, what is F inverse of inverse? It is F. So F maps closed set onto closed set. Okay, so this is true. Option 2 is true, option 1 is true. F is non-constant holomorphic function on omega, then F inverse K is compact for every compact set K in C. Let us look at this one, third option. So let us take Fz is equals to e to the power z, which is e to the power x into e to the power iy. Let us consider this one. X belongs to C such that x belongs to complex such that x is equals to C. Okay, sorry, z belongs to C such that x is equals to C, means x is constant, y is varying, so some vertical line. Okay, so obviously this is, so you can see f of L is a circle centered at origin and radius e to the power c. Okay, so now let us say K. So K is the circle, K is compact. So F inverse K is basically L. So L is not compact. So this option is also not. So this option is also not true. So this option is not true. But uh, but if for a non-constant, so if for a function f, image of, I mean, so let us say f such that omega to c is holomorphic function, so that f of omega is compact, it means f is constant, because f is an open map, so it will map omega to an f of omega will be open. So f of omega cannot be compact, hence it has to be constant function only. Okay, so we are done with the today's assignment problem. Any doubt? Please let me know. So if there is no doubt, I will close the session and we will meet on next Sunday, not Tuesday, Sunday. So the TA, whoever is taking this, whoever is taking session on Tuesday, he has already uploaded the video on the YouTube. So everyone can go and see that one video. So the next, so from the next next class onwards, the session will be on Sunday only. So for this week only, I have taken this class on Tuesday. Okay, fine. So I will close the meeting. Okay, thank you everyone.